Okay.
And this involves painfully refreshing YouTube while I
I
check
see.
that I haven't messed up anything.
Okay, so I should not open YouTube right now.
Oh, this is fine. I can hear myself, so which means we're live. Hey everybody, thanks for joining me back after the break for this series where we go through top Kaggle solutions. This week, as you know, I work with many great people at H2O.ai, and anytime I struggle to understand something, I can just ping anyone on Slack. So since I don't understand Tabular at all, I pulled one of our best at Tabular data, Tariq Hussain, who's a customer-facing data scientist here at H2O. He's also Kaggle master, Kaggle competitions master.
Yeah,
His rank has peaked in the top 500 as I was just sharing my screen, and he's won a lot of medals in tabular data. So we'll be discussing his solo silver solution and understanding his expertise as well. So thanks for joining me, Tariq, for the live stream.
thank you. Thank you very much, Sanyam. I've been to your videos previously and they're great. And I want to collaborate together. Yeah. So let's see how this goes. And
Oh,
this is just a, just like a very, I should say, good introduction. Because I have not done a lot as compared to the other H2O leaders, H2O grandmasters, but trying to be better every day. Yeah.
no, people can see in your Kaggle profile, you're also back on the competitions now. So I'll try to keep inviting you back as you win more and more medals, hopefully.
Great, great. Okay.
So we can probably start by talking about the competition, and I'll probably also point out to the fact that you've medaled in a somewhat similar competition, and you've won a lot of medals in tabular-based competition. So was that the reason for you selecting this one because it's similar to your expertise?
Yeah. So being a tablet competition, I feel it provides an equal opportunity to everyone. So in NLP or computer vision related problems, what happens is like people with a big machine can overcome and train a larger model, and you cannot do much with it. So, but when there is a tableau data competition, the magic lies in the feature engineering, the magic lies in exploring the data in EDA. So I really enjoyed doing that. And I think over the last 3-4 years, participating in different competitions. So I've developed a fair understanding of what will work, what will not work, how to set up the pipeline and everything. So that gives me a good, I should say, familiar space to work with. So I enjoy taking part in them. And I think in a very similar competition happened, which was mechanism of action. So in which I got the gold medal as well. So that is also related to cellular data and cellular structure. So it was also tabular and multi-target like this one. So trying to utilize and use some learnings of this one and map it there.
Awesome. Thanks for that. So, what I do usually is I set up the problem statement. Basically, I make sure that I've understood it correctly. So, what I'll do is I'll try to introduce it, and you can correct me if I'm wrong anywhere. Because I became an expert in this overnight when I
Okay.
studied all of this. Um, I also want to point out to our audience that I've been mentioning the community at h2o.ai. So the forums are live, and if anyone from the audience wants to sign up there or hang out in the forums, the beta is open to anyone watching the live stream. So this is the link to join that. Um, all right. So as I understood, it's about understanding the variance between DNA and RNA measurements, which means genetic measurements. So I tried to understand a bit more about it, and then I found this image, and I only knew a few words from here and there. And after
Yeah.
a few kernels, I quickly understood that this was a tabular problem with the main challenge being that there are a lot of columns there. I'll pull out an EDA kernel real quick. But the main challenge was there was a time series component as well, which was a bit misleading. Some people used it, some did not. And the goal was to use this data from 3 or 4 patients, which was the HSPC cells data. And
Yeah.
based on that, you could divide the problem into two different subsets, and you had to make sure you could predict the covariance based on this. Is
Yes.
this a correct overview?
So That is in line with it, but it has like it is unique in this aspect that there are two components of it. So when you follow molecular biology, you know that okay, DNA will form the RNA, RNA will form the proteins. So what they are doing is they are trying to use the laboratory simulations and real donors data. So they have collected it and they have mapped each of these through some transformation like TF-IDF transformation they have done on their raw data, and then they got these numbers which links up to the DNA to RNA sequence and RNA to protein sequence. So what they want to do is they want to see whether they can extract some underlying patterns, because doing all of this exercise is very time consuming process and it is very research like I should say research expenditure, heavy expenditure process. So they want to use machine learning out of it, and they can see whether if something is working in similar direction. So that is why they were interested in correlation metric. So if something is working in similar direction, then they can quickly select and move on to the next targets. So they were mapping this data from DNA, and DNA was the input first sequence which they used, and they wanted to predict the RNA sequences correlation through correlation. And they also had another target, which is protein. So in which they are using the RNA sequences as the input and trying to predict the protein sequences. So it is a multi problem in one problem. So it was really interesting. And another challenge was that both of these targets were multi-target, so you will have to optimize for each of the target. So people try different mechanism and methods to do that, because in the protein section we had, I think, more than 23,000 targets only. So in the RNA section we had 140 targets, but in the protein section we had 23,000 targets variable only. So it was really like a unique competition in its own.
Thanks for correcting my very incorrect introduction. That makes sense. I also found this post, which is in line with what you were describing, and we can further just give an intro through this. So, as you said, the problem can be divided into two subcategories, which includes the DNA and RNA prediction. And
Yeah,
most people basically in the write ups, you'll be seeing multi iome and I don't know
side
how to
sex.
say this, side
So
sec.
multi-arm and side sex are two different kind of, you can say, microscopic lens through which they have like got these sequences and evaluated them. So then it is divided into multi-ohm target and side sec target. So these are some instruments which they have used to gather the data.
That makes sense. And this post also mentions that there was some transformation applied for both of this. And based on this, you have to predict the outputs and get this gene expression for both the categories. And most people ended up dividing their problem into two different categories because, like you said, there's a lot of features in one and not in one.
Yeah,
And
and
we'll be
both had different weightage also. So in the final evaluation, so multi-ohm and side-sec both have different weightage based on the number of genes they are evaluating. So not every gene were evaluated, not every cell were evaluated. So some selected which they have mentioned already in the evaluation data which they shared. So only those were evaluated. And I think side-sec had a 75% weightage as compared to multi-ohm. So people trying to optimize both and trying to maximize the leaderboard
mm,
positions. So I also segregated the problems into two. So I built separate models for side-sec and I separate model for multi-ohm, because target variance was also there. So multi-ohm had a lot of sparsity in their target. So a lot of zero values are there. So you have to deal with them and you have to like transform it, pre-process it into a lower representation. So a lot of people use truncated SVD for that. And so it was a mix of multiple approaches. And if I will talk about mine, so I've shared it on the Kaggle also. For SiteSec, I also used individual models for each of the target. And that was really one of the boosts which I got in my final ensemble of different models. So uh, I think I tried it in the last week only, that, okay, let's build individual models and use only the correlated most important features, so that it can only focus and optimize on individual targets one by one. So I used the Kaggle GPUs and trained the model on with Tabnet, LightGBM, XGBoost, and CatBoost, everything.
okay.
So yeah.
We'll just come to a solution, but I'll probably just highlight a few more things from a few EDA kernels. And I also like to look at the leaderboard just to understand some discussions because people are mentioning scores. So the best score achieved was 0.775. Higher is better for
Yeah,
Pearson.
yeah,
And if you scroll down a bit, you don't have to scroll a lot. Tariq is on the 43rd
yeah, yeah.
position. And surprisingly, you didn't shake up at all, right?
Yeah, yeah. I did not shake up. I try to minimize my shake up in all of the competitions. So yeah, luckily I did not shake up a lot. I was expecting to be in this range only because I knew that okay, my solution is not up to that gold level right now because I was not trying to improve. I was not able to improve my public leaderboard, and difference was already 2%, 0.02%. So I knew that I cannot beat that, but I should be able to keep my silver position. And luckily, I did not shake any places up and down, so it was good.
The reason why I mentioned that is because all of the teams moved up and down quite a few positions. And it's awesome to see that your score was permanently fixed both on private and public.
Yeah, yeah. So that was a good point. And if it had moved in the positive direction, it would have been better.
It did not move down. I was trying to point out that. I'll also highlight that Dimitri Larko's team also finished ninth, who's also from H2O.
Yeah,
Um, So I wanted to highlight a few things from this kernel. Half of them, most of them have already been covered by Tariq, but this is by a kernel by Ambrose who writes awesome kernels. And the summary in short is that there are a lot of columns, and if you don't apply PCA or SVD, basically, if you don't cut down the number of columns, they won't fit in your RAM at all because there are just so many columns. So you'll see a lot of techniques like SVD being mentioned over and over again. Some people have used ridge regression, some have used UMAP. All of these are basically to cut down on the number of columns and also to construct some features.
yeah. It is surprising to find there are some columns which are not changing at all. So they are not adding any values at all. And I think there are thousand such columns like that, more than thousand such columns, which are just blank or zero value in all of the rows. So no use of. But finding those columns was another interesting challenge. That because you will have to load all the data points. So luckily, someone shared the list of those columns in the forum.
Uh, thanks for adding that. I'll also use this diagram to basically mention the overview of how the problem is set up for all the three and fourth donor. And someone had pointed out that three donors are men and one is woman. So some people use that info as well to relevance. But this is the overview of the competition data once again.
Yeah. So you can see the evaluation is also different. So this problem tested everything. It tested your time series, it tested your multi-target, it tested your feature decomposition skills, and it merged everything into these two sub-problems. So here you can see you have a unseen donor as well as unseen day in the target for both multi-ohm and side sequence. So there is an unseen donor which is donor 4, and there is unseen day which is like a day 7 for side sec part and day 10 for multi-ohm part. So this problem was like completely unique in its own way.
So when you started, and I believe you started in the last month of the competition, how do you suggest ideally approaching something like this? Because there are like so many columns. How do you understand what's going on? Do you look at public EDA, or how do you proceed?
So for this competition, I mostly go with the public EDF at first. So in the first week, I just trying to understand and set my own baselines with public EDF that, okay, what is working in the right direction, trying to change something on the public EDF and see the impact of it so that I do not waste a lot of time, build my own pipeline. So I try to build upon base of that. So I know that, okay, your group fold by donor will work. I knew that, okay, MLP will work, so multi-layer neural network model will work. I knew by that okay, tabnet will work, but I used tabnet in my previous competition, which was the gold medal competition. So I knew that okay, how I can tune better tabnet. So my single tabnet was also able to achieve 76.8 or something on the leaderboard. So I knew that I can train a good tabnet model. So I set my baseline with that. So And then you can see that, okay, some people pointed out that SVD will work for multi-ohm, PCA will not work for multi-ohm. So a lot of these things get clarified in the first week itself when I participated. So
Sorry, I
my,
was just trying to point out that 0.768 would also be somewhere in the silver range. So that would just be one model. And as you lead people, of course, this is Kaggle. So many ensembles were used, but the single model you mentioned could have also been a silver model, I assume.
yeah. So tablet single model was getting 812 on public and 768 on private. So it was a good model. So I kept it in the ensemble. And as I mentioned, so if you I had not been through the public EDI and kernel, so I would have scratched my head how to load the data because there was already pre-processed data. Someone shared it in the forum. So it's always when you are starting some competition, try to spend some couple of days or weeks to understand, okay, what is working, set your own pipeline. So I never do a just fork and run. I always try to do a fork and change something and then run because fork and run is already there shared. So you want to add something more to it, right? So I always try to change something like maybe I can add more layers, maybe I can add some aggregated features, maybe I can remove some of the features, see what is working. So my first week goes around that experiments only, that okay, let's see, and we can decide on the direction in which we want to move, whether adding features will work, whether removing features will work, whether adding layers will work or not work. So yeah, that is how I approach this.
Thanks for sharing that. I found this discussion, which I think you were pointing out. So I understand this was a challenge because there were a large number of zeros, and some people found that discarding them was useful. Others used log one p transformation, where you basically add one and take a log of it, so that it doesn't give you an error because log zero doesn't exist, right?
Yeah, yeah.
So that was also like a major discussion in all of the solutions, why some people use log 10, some just discarded the columns.
So there was this data which was shared late in the discussion, which was like an raw data which the organizer shared. So that raw data they transformed with a log 1p and TF-IDF transformation. So they were trying to regain that transform with inverse transformation, doing some kind of operations. Some people were able to succeed in that. Others just used the original shared data. So I did not try anything on the raw data which later was shared because I know that okay, I'm running out of time and I had my work also going on. So I have built my pipeline on this and it is working good, not that bad. So let's focus on this. Yeah.
I'll do a quick refresher for anyone that doesn't know TF-IDF because I did not know it until yesterday. I did know it. I had to remind myself. So usually when you're working with a lot of data, you have to understand the importance of different things. So TF-IDF is basically it involves dividing by the number of frequency of
So it is
occurrences.
term frequency, like how many times that term is appearing with inverse document frequency, which is like in how many documents that term is appearing. So in the genes term, it is like in gene representation in how many cells or whatever they were collecting, how many times this value was observed divided by how many observations we were taking. So they have transformed it in that fashion
Okay.
with like a log.
Thanks for clarifying that. Um, I'll also the reason everyone why I'm going through this is because all of the solutions just mention these terms, and I was new to it. Maybe everyone just remembers everything. Um, the other two were PCA, although I found more people were using truncated SVD. Could you please help us understand the difference between these two, and why is TSVD better than SVD?
So initially, people tried PCA, but someone tried SVD, and they found that SVD works better with the sparse matrices, so sparse values. And everyone observed that okay, in these components, both the site-sec and multi-ohm, the data is already sparse. So why to go with PCA when TSW is there? TSVD is there for the sparse matrices, and it was performing well also. So initially, people started with PCA. I also started with PCA. I think my two kernels ran for like 9 hours complete to generate the PCA components. So because it was a lot of 2 lakh columns for multi-ohm, so PCA computation is also really extensive. But then I went on to like TSVD, and it worked well. as compared to PCA. But in some of my ensembles, I used a mix of PCA also, like top 60 components, and majority of the SVD also.
Okay, that makes sense. One last drama I want to point out from the competition. There was a small leak in the public test set, which was fixed, and basically the leaderboard was rerun, as I understood. But there was also this drama that happened.
So here what happened was like for one user, one donor, entire data set in test was a replicate of like their data in train. So people know that okay, this data is leak, and they were just copying it from the train set and pasting in the test set and getting good scores. So it was pointed out to the organizers, and the organizers took couple of days to decide on what to do. So they decided that okay, this data will not be evaluated, so you can train your pipeline in the same fashion, just that these rows will not be evaluated in the private leaderboard. So everything remains same, so not much hamper was done in this. So this was fixed right on time, so people had good time to like recalibrate and re-experiment their models. So this was good and pointed right on time.
Okay. Um, Apart from that, one more thing that I totally forgot. This is also an interesting discussion because when you're applying SVD or other such techniques, the columns get converted into something else. And then Ambrose pointed out that some of the column names also have some info encoded there, so you have to be careful with that as well.
Yeah, so this information came later. So we were already like on last 3 4 weeks only, and then this information came that okay, there are some genes which are mapped to the targets also, and their names are interlinked. So probably these features can be directly linked to the target itself, and that is what people did. They tried to keep these features as additional features, and they truncated the data, but they added these features also, so that for individual targets these features add some value to it. So I think I used at the end 84 columns like this,
Okay.
where the gene names were matching to the targets, and just use them as it is.
Okay, that makes sense. So, is there any reason you didn't use all of the columns, or maybe you didn't find them useful?
So there were some columns, as I mentioned earlier, that were completely useless. So I discarded them. Then I truncated and used them as SPD, the remaining ones. And these columns were added on top of that. So I used them in the PCA or SVD as well already, but then added these features also on top of it. So these added some additional value to it. Yeah.
Okay. Now, a few more questions before we start with your solution. So, how are you evaluating which columns are useful or not, just by using the importance plot from the different algorithms? And then, how would you suggest approaching feature engineering or and cross validation as well? So, three questions: how are you discarding the columns? And we can start with that.
So in this column, in this competition, I should say, in this competition, the majority was how much variance was there. So some columns were discarded on that only. That okay, 99% no variance was there. Only 0.1 or something variance was there in some of the features. Some of the features were completely zero. So no point of keeping them as well. So those features were discarded. What was your next question?
How did you approach feature engineering? So there were a lot of columns, which means there was a lot of truncation involved. But after that, feature engineering.
So after that, we know that okay, 50 to 100 components from the truncated SVD and PCA were working. So what I did, I trained the multiple models with different layers. So in some models I kept 3 layers, some models I kept 6 layers, and used different components also. And different components, as I should say that I in some models I use 70 components of the SVD, in another I use 100 components of the SVD. So I was trying to differentiate and make it more robust, that okay, some noise can be cancelled out in this fashion when we train multiple times with different thing, different learning rate or different number of batch sizes. So I was trying to reduce that shakeup, and that helped. So I trained, I think, 6 7 different models in this fashion where just components were varied. Another important thing was that we were able to get some additional benefit by binarization of the inputs. So binarization means that we were trying to binarize into 0, 1, the upper ceiling, lower ceiling, and then truncate it. So that binarized and SVD also helped. So I trained some model on mixing both also. So binary SVD as well as the normal SVD. So it
Okay.
was like you can imagine a lot of different ways to process. Some people were trying TSNE, some people were trying CMAP, UMAP, but I think TSVD worked the best. Yeah.
Okay, that makes sense. And finally, how did you set up your cross validation for this?
So in this competition, particularly, I know that there was a time component as well, and there is also a group fold component. I use both of them, but apart from that, I also added k-fold shuffled validation because in my experiments, I see that it is also correlated with leaderboard. So I kept that k-fold cross validation as well. I did not discard it, but I use in the low weightage. So I use like if I am giving 7 weightage to my group K fold, my K fold will only get around less than 50% 3 weightage or something like that. So I used it, and I think cumulative of everything, I was able to avoid the shakeup. It would have been better. I should have if I had moved up, but yeah, I'm happy with it.
Okay, I think sticking to the position is also awesome. But maybe we can learn from Chishan, who always shakes up to first position, and I'm always trying to ask him. He doesn't share any secret.
Yeah, yeah, that will be a great session for all of us.
Yeah.
Another
Uh,
important thing was that there is a day feature, which I think most of the public kernel just ignored it. But I think added these features in this individual models, which is like the site sec individual models which I built, that helped the model like gain a big advantage. So day feature was able to give the tree-based model more segregation, and it was able to see more features segregation. So I think I was not able to beat 813 on public without that day feature. But when I used that and added it to individual models, I shoot up to 8142. So that was a really big jump.
I think during the towards the later half of the competition, there was also this discussion pointing out to how it's also a time series problem.
Yeah, yeah. After reading this only, I got to like think about how to add this information. So there was a time series split which people can use, but providing that this data is changing a lot, and we do not have enough number of days to validate upon. So it is a good strategy, but also it can prove risky if you only use this one. So that is why I added other folds also, group fold and K fold, but I also added the day as a feature. So yeah, I try to minimize the variance as much as possible.
Okay, that makes sense. I think I'll now that we have set up everything and you've already covered parts of it, I'll just request your help to understand the complete solution that you had created for this problem.
Yeah, yeah.
So, if you could just give a overview of summarizing everything that you ended up using for your final pipeline.
So as you can see, so a lot of time devoted to data preparation, what will work and what will not work. In this part, I only evaluated, okay, which models we can train, what features we can use, what kind of components we will be making. For example, whether we will be making PC or whether we will be devoting time on truncated SVD. So initially, a couple of weeks, my time devoted to that. And CV scheme was already shared that, okay, group K fold will work. So I stick to that, but I did not limit to that. So I tried to explore other options also, like trying to increase number of folds, trying to see different representation with different seeds and everything. So in that respect, I was able to set group K fold and K fold to be part of my final pipeline. And in the modeling aspect, I should say that neural network was the majority of it. So because it was a multi-target, so neural networks can work well. When tree-based model cannot work well, if it can work well, but it will need a lot of computational resources, and probably you will run out of that in Kaggle environment. But neural network was able to do that. So a lot of multi-layer perceptron single like I was trying to increase the number of layers. I was trying to use ResNet kind of a structure. So it was a mixture of different MLPs model and with different number of components and different number of feature representation, whether it was binary or just raw feature representation. And then tabnet and like GPM based models were also used because.
Sorry, sorry to interrupt. Can we dig into a bit of how did you design these architectures for MLPs, or were you just trying vanilla architectures with more focus on
So it,
pre-processing?
it, it's developed from the Ambrose one. Ambrose
Mhm.
shared the EDA, which he was able to get, I think, 806 or 807 something on leaderboard. But with my slight tweaks, I was able to take it to, I think, 813. Yeah.
Hmm.
It was not slight. Like in the last week, I was able to take 813. So it increased in iterations that, okay, what will work? What kind of learning rate will work? What kind of batch size will work? So initially, when using 256 as a batch size, I was not able to gain much performance, but 512 helped a lot. So then retrained all the experiments with 512 that, okay, this is performing better. So a lot of these experiments I did based on the public one, which information was shared. Another information which was shared was that CatBoost was also working. So
Mhm.
CatBoost model is a tree-based model. So if that is working, then probably LightGBM or XGBoost will also work. So the point was, how can you use them? So someone shared that, okay, let's transform the targets also with a SVD. So 23,000 targets variable were there. So let's transform that into also SVD. Let's predict the transform targets and re-inverse them to the original targets. So I think majority of people did that for multi-ohm. So where they transform the 23,000 targets into 256 or 128 components and then mapped it back to the original target. So a lot of these kind of, I should say, iterate and make better was the way to do it. That, okay, you establish something and then you try to improve something on that. So in that aspect, I've finalized all of these model that, okay, tabnet will go into my final pipeline, like GPM will go into final pipeline. For example, with sitesec, I knew that, okay, we can extract the important features based on correlation values, based on feature importances. So I knew that, okay, sitesec, that will also add value, but not for multi-ohm. So for sitesec part, individual models will also go into final pipeline. So in this way, I think I was able to ready with my final end-to-end pipeline. And then last week I trained only ensembles. That, okay, my all models are ready. Let's try to optimize weights. Let's try to find how much component, how much weightage we should give each of them. So yeah, I think I had around 50 or 60 submission just to optimize that ensembles.
Okay, that's quite a lot. Okay.
Yeah, because I think I knew that, okay, this is something which will work on private also. So let's just make it better. So I was not chasing very high number. I know that the a private leaderboard will be a lot lower than what we are seeing on the public. So yeah, just focused
Makes
on
sense.
trying to make everything robust.
Makes
But
sense.
in this competition, another thing was there that if you had a teammate, chances of you doing better would have increased. For me, also, it would have been increased. But yeah, I tried to do it alone, but our teammate would have been good.
Okay. But you did get a solo silver, which is also quite hard these days. Considering also this was a like quite competitive competition. It had a nice number of teams.
Yeah. And this competition also saw like a very adverse side of Kaggle.
Yeah. Um, yeah, I think it's not fun to go into too spicy things. Um,
Yeah.
but okay. So anything else you want to highlight from your solution that we might have missed?
Uh, No, I think we are good on this aspect. I think I would have explored this pi boost earlier. So it was shared later by this log likelihood user KSS. They won the gold also. So this pi boost is a new one. I have not explored it much, but it works better than cat boost and it is supported for multi targets as well. So I think my key takeaway from this competition was this library that I will try to use in some of the future competitions. So I have not explored it at all right now till now, but I think this has a good potential to be part of Kaggle competitions. Yeah.
I did not know of this, and I think it's underrated. It just has 43 stars, so maybe everyone
Yeah.
learned something new today.
Yeah. So I also it was shared by this user only KSS on his winning solution section that they have used this Pi boost and they get big benefit from them. So yeah, that was a big takeaway.
Awesome.
And yeah, I think that was part of my solution.
Okay.
That's all.
Thanks for sharing that. Would you like to stick around for going to the other top solutions, or should we conclude our interview here?
I think it is fine. So I can wrap it up. No worries. And I
Okay.
will let you continue with your section.
Thanks.
Yeah.
Thanks for joining the live stream. I'll quickly point out your Kaggle profile where people can find your LinkedIn profile and they can connect with you. So if you're watching this, it'll also be in the description and in the pinned comment. You can find Tariq on Kaggle and connect with him on LinkedIn. Anything else you want to point out? I'll also have your solution link there. Anything else?
Okay. No, I think we are good. Yeah.
Okay. Awesome. Thanks so much for joining us and for helping us understand the solution.
Thank you. Thank you very much, Sanyam, for having me. It was great. Yeah.
Okay.
Thank you very much.
Awesome.
Bye.
Bye bye. So for everyone that's still on the live stream, I'll continue going through the top solutions, and I wanted to cover Tariq's solution first because he's the chief guest and he was also helping us understand the problem. So now what we'll do is we'll go through the top solutions. I'll take my headphones off because I don't need to hear Tariq. And in the next half an hour or so, I'll try to cover the top 10 solutions. And as you all expect, I usually am very ambitious, is covering more and more solutions. We might go over time a bit. We'll see how that goes. So just to point out, the winner had also open sourced the solution, and you can find the link in the write up. The reason why I don't share any of these links is because they're quite lengthy links, and I can only highlight them like so. So all you have to do is just go to this competition, and you'll be able to find all of these. But now let's continue with understanding the winning solution, and from here on, we'll go in sequence of all the top solutions. So they have a nice overview for both the approaches. So for multi-iome, they had this model overview where that uh, described their pre-processing and post-processing in detail. So let's look at the input pre-processing, and they'd also done target pre-processing. So like Tariq mentioned, many people design this approach where you had a large number of target columns as well. So you would compress them and then predict based on the truncated columns, and then you would apply a form of reverse engineering where you get back the original y column. So you have a y column which has a lot of features. You compress it and you train your model on that. You get the outputs based on that, and then you apply some form of transform which gives you back the original y or y hat column where you're supposed to make the predictions. So that was also part of this approach. um TF IDF was applied to chromatin accessibility, and they had done this in two steps. Basically, divided TF IDF values by row wise non zero median values, and that performed a dimensionality reduction on this data with TSVD into 128 columns. The other approach was convert non zero values to 1 and then also apply a dimensionality reduction, and then that becomes the input that goes into the model. And from the outputs, you have this target pre-processing that I just mentioned. Let's take a look at that. So for that, you do the following steps. Not you, the winner did the following steps. They divided the count data by row wise non-zero median values. Now, one thing I've learned, and I think this might be obvious to a few people, but there's a lot of z-scores, median values, subtraction, addition, division involved. And as I understand, it's part of just experimentation and a feel of what works well or not. So that's my understanding, that you usually perform such transformations where you take the mean, take the median, calculate the z score. Z score tells you how different the column is from the mean values, and you basically add, subtract, multiply, divide with these values. So that's a lot of transformations that we'll see again in the next few solutions. um but basically you had this non-zero data now, which you would transform with log 1p, and then you would add the value 0 at 0 with tsvd values, and then you would normalize the row wise data, subtract the medians, and then reduce the uh, dimensionality. So you don't just apply TSVD on the target columns, you perform the following steps and then you compress the data. For the model, they have these what they call LB layers, which is a linear block, where they have a GLU column. And if you want to remember the graph of GLU, this is what it looks like. The orange line is ReLU, and the green line is ELU. So GLU has a graph like so. And if you're interested, you can just look it up on papers with code. They have a nicer explanation. But for our understanding, it's an activation function with the following behavior. So in their model, they had these layers where they had a GLU layer followed by a layer normalization, dropout, and then a linear layer. So all of this pre-processing that we've applied right now, it's just the pre-processing to the data set, gets inputted to these linear layers, passes through a linear layer followed by a LB layer, and it's done a bunch of times, 2 times to be exact, and sorry, 6 times to be exact. And after that, you have the outputs feeding into post-processing layer. After that, you of course make the predictions. So what you do is you calculate the MSE loss and you transform the data back into the original space, add a column-wise median, and then calculate the correlation loss. So this was just for the first half of the problem, which was multi-ion. And let's take a quick look at how did they approach the site-sec problem. So this looks quite similar in some ways. In the overall approach, it looks similar, but the fine differences are that the metadata and input stats are also utilized that were fed to the model along with the pre-processed inputs. And here the RNA data was being fed because this is a site-seq data. For input pre-processing, again, it's the RNA data that's being fed here, but it's somewhat similar in the sense that I won't go through all of this, but it's basically a computation you're applying where you're dividing the data with median values and then transforming it, and then you apply the following pre-processing where you're imputing the zero values and you're subtracting the column-wise median, and then you perform a reduction in data which is fed to the model. So they apply all of this pre-processing, and that's what goes into the model. So when they say input pre-processing, that is this approach where they transform the columns and then truncate it. They also select the highly correlated highly correlated columns. So as Tariq was mentioning, a lot of columns were useless, so you probably wanted to discard those. Again, they did some target pre-processing as well as we had just discussed, and the model, from what I understood, was very similar to the earlier one. If you look closely, you can probably tell that there's a difference in the data being fed from the pre-final layers into the linear layers, and here it's slightly different number of layers. From what I understand, winners usually mask out a few details. So a few details are usually left missing because they don't want to share everything. There's a slight difference in the final model is what I understood. So they say for their local evaluation, they'd used a 5-fold CV grouped by donor and day. And for evaluation, they've done a hyperparameter optimization with Optuna. The ensemble use models trained with changing the seed. This is known as seed averaging. It works surprisingly well for a lot of competitions. And the models were fine-tuned only on some batches, which is also very interesting for me to see. Again, the complete code is open source. So if you'd like to check that out, you can read that linked in the write-up. And we'll remember to upload this. I don't see any questions based on this or any discussion points coming up. So I'll keep going in sequence and I'll probably rush through as things get repeated. So this was covered in 2 parts, and Grandmaster Senkin has shared the open source solution as well. So if you go through both of these, you can find the Kaggle kernel, which tells you how you can replicate their winning solution. So the first part of the approach talks about pre-processing. They use the raw counts. They normalized by mean values over features, did a square root transformation, and they standardized this with a z-score, followed by which they did a batch effect correlation. So they take days as a batches, and for each batch, they calculate the column wise median to get a median sample representing the batch. And then they subtract the sample from each sample. This did not improve the scores, but it helped improve avoid risks, as they say. I cannot validate this claim. Maybe you can just try this for yourself and see if it actually helps. Now, this knowledge is embedded in the minds of the winners, and I assume it's just a feel of what they know works well. Enric says hi. Hey, Enric, thanks for joining. For feature engineering, they said they performed PCA and IPCA. IPCA is also, as I understand, a variation of PCA, and factor analysis. For feature selection, they compared by selecting features that are highly correlated to target, and they preferred to select the features that show stable correlation with the target. In addition, some features with the same name as target are included by relaxing the PCC threshold. So they also did some manual, most of this was manual, but they also looked into what was being fed and actually relaxed the threshold as well. Their model, they don't share a lot of details in this write up, but they say it was a multi layer perceptron with 13 layers, and this used Huber laws. They also used a LGB model, and they say MLB performs well and is better when blending with the above. And both use the exact same features. For multi-iome, they say there's nothing special in pre-processing and modeling. Only feature engineering is slightly different. So they use PCA, they use feature. Chromosome was a feature here, and they group this feature according to their chromosomes. And only chromosomes containing more than 100 features were retained. Features on each chromosomes are divided into 3 groups according to their position. And then mean and proportion of non-zero feature values is calculated. Features on each chromosome are divided into 2 groups, and PCA is implemented. Finally, a binary PCA and chromosome feature after binarization, they also use the same method as above to obtain feature of binarized version. So they're also binarizing the columns along. They're basically using binary PCA on chromosome feature. We'll remember to upload this. And the second part of the solution gives us some more insights. So for site-seq, this is an overview of the modeling approaches. You have the raw data that is being fed into light GBM models and two neural networks. They describe here that using GRU layers was also key in some ways. We'll just read that in a second. And they had applied the following pre-processing. So raw data had a centered log ratio applied to it, followed by TSVD and a row by z-score. Now, one thing to note here that Tariq highlighted, but not all solutions point out, is how they discarded all columns, which columns did they use, and to which columns which techniques are being applied. They give an overview of what they applied to some columns, but as you can imagine, the fine details are quite hidden. So it's really to experiment and see, and it's I think it's a craft of it's 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 quite hands-on knowledge, and you have to apply and see what works, I assume. Again, I haven't competed in many tabular competitions or read many tabular papers for that matter. So the other feature being fed is you input high correlated target features, and you calculate the row wise z-score. The third one is a customized process, which I don't think they mentioned here. And they apply TSVD and PCA and then calculate the row wise z-score. This is fed into the light GBM models and the two neural networks. The neural networks have a bi-GRU layer followed by dense layer, and dense layers followed by a bi-GRU layer for the other one. They share some details about the fine nuances of these. For multi, it's slightly simpler model. So the TF-IDF data is fed into all of the following uh, tree-based algorithms. And the other one is the following transformations are applied: centered log ratio, TSVD, and a row-wise z-score is calculated, which is fed into the neural network. So one thing to mention is the tree-based outputs are also being fed into this. And this just has dense layers. So there is no GRU layers here. The fine-tuned process, I sorry, I was checking if this was a customized process, but maybe I'm just confused. So they talk about how they've fed in these features. They use the raw count, normalized based on sample normalization by mean values over features, did a square root transformation, and standardized with z-score. Again, they talk about batch effect correlation. And finally, they calculate the row-wise z-score transformation before inputting to neural network. I think I'll skip the validation because it's already been covered. So for models, they had a they outlined the following. For light GBM, they trained full LGBM models with different input features and then transform the OOF predictions to TSVD as neural networks meta features. So these outputs here are transformed into inputs for the neural network as meta features. The raw counts are converted like so. The raw counts are fed as well, and raw counts with raw target are also fed into the live GBM models. One trick they share is input of sparse matrix of raw count with small feature fraction 0.1. So they apply the features with a zero point 0.1 multiplication. It brings the neural network a lot of improvement. They claim that. Neural networks are basically three MLP layers. We've already gone through this, and they say the trick here is to use GRU to replace first dense layer or add GRU layer after the final dense layer. I assume they know this through just their knowledge and experimentation. And maybe maybe you can experiment and check their claims. I think that's a good overview of the second place solution as well. I don't see any questions, so I'll continue. As a reminder, if you're watching live, please just make noise in the chat if I'm glancing over any details that you want to discuss. So we still have a few minutes, and what I'll try to do is try to get through as many other solutions as I can. We might go over time, which I assume is okay with everyone, hopefully. So I'll try to go fast now. Not too fast. Now we'll go through the third place solution. And they say they had no knowledge of biological field and they still don't know much about it. So this is good motivation for all of us that, hey, we can just use our machine learning skills and probably do somewhere in the top three if you work really hard and if you have the knowledge, right? So to summarize, they share the pre-processing. They use OKAPI BM25 instead of TF-IDF. They used LSI approach, which they have shared here instead of SVD. So as you can see, this is slightly different. They say the pre-processing helped quite a bit, and they did some binary feature transformation for and the other transformations are like, so for each cell, the top 100 with highest expression levels were lined up and vectorized with a gensim to get feature vectors for each gene. They had a Leiden cluster mean feature. I was new to all of these terms, and I'm not sure if these are fairly common, but basically, I read through the links that they had mentioned, and it somewhat made sense. So, from what I understood, they use different approaches and slightly different frameworks to pre-process their data and come up with all of these pre-processed inputs to the models. They talk about the connectivity matrix feature. And they say since muon's Leiden clustering generates an agent adjacency matrix, They also use a 16 dimensional with SVD as a feature. So they use a 16 dimensional column along with the SVD calculated, I assume, on the adjacency matrix as an input. Actually, I'm not too sure what this means. So if anyone anyone understands it better than I could, please let me know. I'll probably ask in the comments after this. I'll comment on this post is what I mean, not the YouTube comments. Yeah, I was trying to read it. It still doesn't make sense to me. Sorry. I'm just confused by this one. Uh, I'll try to continue regardless. So for MLP, they use the ones from public notebooks. The target had been reduced to 128 and they used RMSE loss. For cat boost, the target had been reduced to 128 dimensions as well. The ensemble had 20 MLP and 3 cat boost with various feature combination and CV based weighted averaging. For pre-processing, they shared that they had applied normalized per cell and log 1p, which was shared in the column. And the features being calculated here are quite similar as well. So for site-sec, they used a MLP with similar to public notebook setup. And they use correlation laws similar to public notebooks as well. Okay, that's it for the third position overview. Let's try to cover the fourth and fifth position as well if we can. So for site-seek data, they pre-processed using log 1p to change their raw data. And they had also tried other approaches, but for them, surprisingly, these did not work. For feature engineering, they say it has 6 parts. 3 of them are dimensionally reduced using TSVD, UMAP, and Novels method. The rest are feature selection parts, including name importance, correlation importance, and RF importance. So all of this makes sense. 2 things I'll point out here is correlation importance. They choose the top 3 features that are correlated with targets. And the number of selected features was about 104. For RF importance, they selected 128 features of importance to random forest models. So they used, for modeling, they used a neural network that they had personally designed, trying to do something like transformers. And here they replaced the dot product in the mechanism of attention. They also tried tabnet and RTDL, but these did not work well. Uh, RTDL is a form of resonate like approach for tabular data. I had covered this in one of the paper reading groups, so I know. But if you look this approach up, it's by Yandex Research and it's a nice framework. They had also tried a CNN based approach where they added multidimensional convolutional layer like ResNet. They had an online neural network, a kernel ridge approach, and I'll glance over the other ones because they have already been covered. This probably gives a nice overview of their approach and their final ensemble. So you have the all days data that has been created into 3 folds that is fed into all of these models. And you have the original features, the OOF predictions that are concatenated. And these meta features are further fed into the following models, which then are again concatenated and fed into final MLP, which gives you the final outputs. And as you can tell, they put a lot of efforts into the site-seek data. So they say for multi, they did not do a lot of efforts here. So it's quite simple. The inputs were TF, IDF normalized. A log 1p transformation was applied. The targets were normalized and compressed, as I like to say, using TSVD. The neural network was same as designed above, and the outputs were slightly tweaked to make it work and the correlation loss was used to calculate the gradients here. All of this has been discussed in the previous write-up, so I'm just glancing over the details. I think that's it for the fourth position overview. So we'll continue in our understanding experiment. The title says a beginner part because their Kaggle profile name is a beginner. And the user also mentioned that this was their first competition and they did work incredibly hard and their team got the fifth position. So just as a nice overview, or just as a nice mention, I wanted to point out that if you work really hard, you can also get the fifth position. So we're out of time. I'll probably wrap up with this solution. For data pre-processing and feature engineering, they use the public notebooks. And for PCA, they reduce the dimensions to 128 and use direct features based on absolute correlation. After this, both of the columns are normalized. For the model, MLP without batch normalization and dropout was used. They say trying different activation function and ensembling that was really helpful. And the other approach was using two LGBM models with different data pre-processing, which they don't mention here. They had group K-fold on donor and day. And the final ensemble was selected using OOF predictions, where they had four neural network models to mix with two LGBM models and determine the weight. Again, nothing interesting. I've already gone through this, so nothing interesting to point out in the pre-processing here. I think that's all that was here to learn. So what I do usually as a reminder is I just point out the new things in all the solutions. For multi-iome, they applied the following techniques: TF-IDF, log1p, normalization, PC, and row normalization. They used all of these dimensionality regression approaches, and then this was fed into the MLP. And it had a similar setup, as you can see. Um, okay, so that's it for the fifth position. Should we do one more or should we wrap up here? I know we're out of time already. Okay, I'm not getting any response on the chat, so I should wrap up. Um, I'll mention that the other approaches are also quite different from each other. So I'm glancing over what's been already covered, which is how this was pre-processed or how this was covered. But one thing that I'll point everyone towards is PyBoost, which Tariq already did. So the seventh position says that PyBoost was really helpful to them. I would say definitely please check that out if you're interested. That framework is quite interesting. The ninth position shares how they tried this NLP based approach, and how they tried to apply transformers to this, but it didn't quite exactly work. And finally, they settled on something slightly similar to what everyone has been doing, and they use this residual network after doing all the pre-processing that's similar to everyone. So that's for a quick overview of that. The 12th position also shares a lot of interesting approaches. And one thing they point about the trends in data where they neglected the time series component here. So the short factor was, since this is medical data, Silogram is one of the Kaggle legends, so we should listen to him when he says something, or any of the winners for that matter. But he says since it's just 7 days, these trends could be very small and it could be a temporary trend as well. So he did not use this, but it turned out that they were quite important. Um, Anvesh says carry on. So I'm just giving the overview of all of these problems and probably trying to wrap up as fast as I can. Uh, One thing I'll point out in the last solution from the 12th place solution is I really enjoyed this part of the write up. My job is demanding, so I delegate the work to computers. Whenever I cannot, I minimize the time needed for coding such that I can leverage the fragmented time. And I mainly participated in this competition to learn feature extraction with high dimension inputs and outputs. Um, this is a Kaggle Grandmaster, so of course they knew what they were doing, but it's it's really interesting to see that part of the write up. Um, Someone's asking how can you see the documents I present? I just go to the solution. I just sorry go to the competition and I just open up the different links from here. So if you go to kaggle.com and you look up open problems, just go to this competition and in the discussions tab you can find all of these. The specific reason why I don't share these links is because it's I go through a lot of links and it can be painful to just follow all of them. Um, okay, I glanced or basically rushed through all of the last few overviews, but I think we can wrap up here. I would still encourage everyone to read the top 15 solutions because there was something interesting and something different in all of them. The main learnings to summarize was it was a higher dimensional problem where a lot of columns were useful, some were not. So many people use dimensionality reduction, many people use different techniques. This is one of the first competitions where MLP was useful in tabular data, which was very fascinating. Again, that's something to point out, right? Like if you follow Boyan on Twitter, he's also always saying XGBoost, but I don't think we saw XGBoost here. Um, the other approach or the other interesting thing I learned here, you can also compress the target column and predict on that, and then uncompress that or basically apply a reverse dimensionality reduction and use that as an output. That's also one thing I learned. And apart from that, we saw how performing all of these feature engineerings and then using different approaches together and also using meta models was helpful here. Um, okay, so I'll try to wrap up on that, Mark. Hopefully, this was useful for everyone. Next weekend, this will keep happening every weekend. This top solution reading group, and next weekend we'll go through the feedback prize competition, which should end in about 2 days. So next Sunday at 8 a.m. Pacific, we'll go through this competition. If you join me live, thanks for watching. Or if you're watching a recap, thanks for watching the entire video. Please consider subscribing if you enjoy these and consider joining the H2AI community if you'd like to be a part of that. And also consider thanking Tariq for helping us understand the problem statement overview. Okay, thanks everyone for joining. It's great to be back. It's great to be doing all of these weekly live streams. Sorry, I'll mention one more thing. There will be also two more study groups, so NLP one and a deep learning one that I'll be starting soon. So please keep an eye on for that as well. With that, thanks for joining. Have a great rest of your day.